This demonstration was developed in the context of Unity's 6G project, and especially under Work Package 4, which concerns AI-driven distributed intelligence. The demonstrated algorithm is a work by 4.Infinity and performs intelligent dynamic handover by utilizing AI-assisted signal quality prediction in realistic 6G networks. Let me briefly describe the scenario. The objective is to demonstrate how machine learning can proactively improve mobility management. Instead of relying on the current radio measurements, our approach predicts the future signal quality of the candidate base stations and triggers handovers before the communication quality starts degrading. For the simulation part, we consider a realistic urban environment generated with the Cyana ray tracing library. For the intelligence part, we use a deep LSTM that predicts the next step SINR values from historical measurements. These predictions are then embedded in the predictive conditional handover framework to determine the optimal serving base station. The radio environment corresponds to a real urban area in Eloniko, Greece, modeled using the Cyana ray tracing engine. Coverage is provided by two base stations that implement a complex channel model with multiple propagation paths. The map is colored based on the strongest coverage power of each base station and includes also white areas that are totally out of coverage. In more detail, the propagation model captures the effects of the environment, including line-of-sight propagation, reflections, scattering, antenna characteristics, material properties, and the surrounding geometry. The buildings are represented in gray, while the road network defines the valid mobility area for pedestrian users. Based on this environment, we generate realistic road-constrained user trajectories. As each user moves through the network, Cyana computes the SINR towards both base stations at every position. These sequential measurements are then transformed into windowed time series datasets that are used to train the deep LSTM prediction model. After training the prediction models, we integrate them into the predictive conditional handover framework. The framework is coordinated by a RAT steering controller, which orchestrates the entire process and includes three main phases for each location of the UE. First, there is the data collection phase where the user equipment reports radio measurements to the serving RAT and to the RAT steering controller, where they are stored for further processing. Second, the intelligent module constructs a sliding window of recent measurements for each candidate base station and performs parallel SINR prediction using the trained deep LSTM model. In our case, we will infer in parallel 2 times the BS model. The decision module, after receiving all predictions, has to make a decision about conducting handover or not. This is based on a condition that says, if the predicted SINR for some target RAT is bigger than the predicted SINR of the current RAT by a threshold value, for a configurable number of consecutive prediction intervals, then switch to the target RAT. These parameters provide hysteresis and reduce unnecessary handovers and ping-pong effects. Finally, once the predictive condition is satisfied, the standard handover execution procedure is performed through the conventional signaling exchange between the serving base station, the target base station, and the user equipment. At this point, we can switch to the live execution of the proposed solution to observe its performance on an unseen trajectory. In this animation, we compare 3 handover strategies along the same user trajectory in a real urban map environment. The color of the traveled path indicates the selected serving base station, purple for BS1 and yellow for BS2. Red markers indicate handover events. The left panel shows the reactive handover baseline. In this case, the serving base station follows the actual best SINR at each position. This gives the ideal serving decision, but it can trigger frequent handovers due to multi-path effect and shadowing. The middle panel shows a soft, proactive handover strategy. Here, the RAT steering controller triggers a handover when the predicted gain over the current RAT exceeds the 1.5 dB. The right panel shows a hard, proactive handover strategy, using a stricter decision rule. The handover threshold is increased to 3 dB, while the handover condition must remain valid for 3 consecutive steps before the switch occurs. It is obvious that both predictive variants outperform the reactive baselines, as they eliminate ping-pong effects. In addition, increasing the handover threshold reduces the number of handovers, while the hysteresis-enabled scheme balances the trade-off of strong coverage and stability by demonstrating smoother connectivity. During the next months, the proposed algorithm and framework will be extended in a multi-rat scenario, cellular and Wi-Fi, and then integrated into the proof of concept 2 about AI/ML-based multi-rat resource optimization on top of the time-sensitive Unity 6G architecture. Thank you for your attention.